So here we have one more example dealing with a telescoping series. And here we're going to determine if this series converges or diverges. And if it is convergent, we will hopefully find its sum. So here we are looking at the sum of ln of n divided by n plus 3. And here it is going to be telescoping, but you'll notice it's not going to be partial fractions like we saw in the last one. But we do need to set this up so that we do have sort of a cancellation similar to what we saw in the last one. So here there is something that we can do using properties of logarithms to split this up. We get that on the right hand side we would have the sum starting at 1 of ln of n minus ln of n plus 3. So now that doesn't look exactly like our last example, but it is similar enough that we are going to achieve that telescoping effect in our partial sum. So let's go and actually look at our partial sums. And the first one, the first partial sum here is going to correspond to our counter being equal to 1, and then we will have our counter being equal to 2, and so on. So if little n is equal to 1, our first term is going to be just ln of 1, which will be 0, minus ln of n plus 3, which will be ln of 4. Okay, and so those are the first two values in the first term. And now we take a look at what happens if little n, our counter, is equal to 2. So now we have ln of 2 minus ln of 2 plus 3. That'll be minus ln of 5. And we want to keep going with this. So the very next term is going to correspond to n equal to 3. And we're going to get here ln of 3 minus ln of 6. So let's see if we can get one more term there. So what happens if n is equal to 4? Well, our very last term is going to correspond to ln of 4 minus ln of 4 plus 3. It'll be minus ln of 7. Okay, and this summation is going to continue on and on, but it is going to stop because, again, we're looking here at just the partial sum. So now let's go look at the last few terms in this partial sum. And we're going to do something similar to what we did in the last example. We're not just going to look at the last term, we want to look at the last few terms. And specifically, since we looked at the first 4 terms this time, let's look at the last 4 terms. Okay, so now we have our terms that we started with. Let's sort of clean that up a little bit. And we have our terms that we're going to finish with. So we end when our counter little n reaches big N, and that's going to be our very last term. And then we have our second last one is going to be at capital N minus 1. We have capital N minus 2 and capital N minus 3. So now let's take a look actually at what these terms are. The very last one, when our counter reaches capital N, we're going to have ln of capital N minus ln of capital N plus 3. Okay, that's going to be our very last term. The second last term will be ln of capital N minus 1 minus ln of capital N plus 2. Okay, there's our second last term. Let's take a look at our third last term. We now have ln of n minus 2 minus ln of n plus 1. And then when we get here to the fourth last term, we have ln of n minus 3 minus ln of n itself. Okay, now you may be wondering, in this case, why I put 4 terms down at the start and 4 terms down at the end, whereas in the last one we only did 3. And the answer is, for this one, the pattern is actually going to be a little bit more difficult than in the last one. Okay, the pattern in the way that these terms cancel out. So first off, let's go through one by one. Let's see which terms cancel and which terms do not. So if you look through these terms, you'll notice that at the starting ones, the only term that's going to cancel right away clearly is this ln of 4, but not with anything from here or with anything from here. It's actually going to cancel with this term that is quite far away. Okay, it's going to cancel with the first term, not in the next set of brackets or even the one after that, but it's going to take sort of the third pair of terms after that. Okay, so now what's going to happen with ln of 4? They're gone. Okay, they cancel with each other. And then what's going to happen with this ln of 5? Well, it's not going to cancel with anything from here or with anything from here, but it would cancel with something from the very next set of brackets. So here we can cancel out that ln of 5, okay, even though we essentially skipped that term. So the ln of 5 is gone, and the same thing will happen with this ln of 6 and with this ln of 7. However, you will notice that this ln of 3 would have canceled with something that would have come from far before, so it does not cancel. And the same with this ln of 2, and the same with this ln of 1. So those three terms are going to remain. Now let's go to the end of our partial sum, and we'll notice here that right away we have this negative ln n will cancel with this ln of n in exactly the same pattern. Okay, and so they're both gone. But now let's take a look at this term here. For example, it would cancel with this one, so it does not cancel. This one as well would cancel with term over here, so it does not cancel, and the same with this one. So which terms here actually do cancel? Okay, well again, let's work backwards. Remember that this term here canceled with this term here. So it would actually be that this term would cancel with a term from that pair of brackets. Okay, so that term is gone. And this term here would also cancel with a term from before. So that term is gone. And the same with this term, it would also cancel. So the only terms that do not cancel, in a similar pattern to what we started with, the only terms that don't cancel are going to be these three terms. Okay, so now let's actually just take a look at what happens with our partial sum. So our partial sum, S sub n, is simply going to be ln of 1, okay, which is 0, but it's going to be plus ln of 2 plus ln of 3. And then we also have these three terms at the end that don't cancel. So we have minus ln of capital N plus 1, minus ln of capital N plus 2, minus ln of capital N plus 3. So it's not quite as nice as the last one. Okay, we don't end up with only two terms. However, it is definitely an expression that we can take the limit of. So let's go and check what happens if I now do the limit as the number of terms here, capital N goes to infinity, the limit of S sub n. Well, that's going to be the limit of all of the terms that we had right here. Okay, and so now let's try to put those in. We have ln of 1. Let's actually drop that one. Okay, we know that that one is 0, so it's just going to be ln of 2 plus ln of 3 minus ln of capital N plus 1 minus ln of capital N plus 2 minus ln capital N plus 3. And that's the limit that we're looking to do. And really, these terms are all constants, so they don't really do anything, but this term is going to approach minus infinity, and so is this term, and so is this term. So all of them approach minus infinity, meaning our entire limit is just going to go to minus infinity. Now, what does that actually mean in the context of the question? Well, that means, first of all, that this limit just does not exist. And if the limit does not exist, that means that the series that we started off with, starting at 1 and going to infinity, ln of n over n plus 3, okay, that series is divergent. Okay, the actual sum of the terms continue to, well, increase as a negative value, and they do so without bound. Okay, they approach negative infinity. They are or that corresponds to a divergent series. So that is telescoping series, and we've done a couple examples together. In the next section, what we're going to do is we're going to take a look at geometric series, okay, which is again a very specific type of series, and we're going to be looking at when do geometric series converge and when do they diverge.